Assalamu alaikum. I am Dr. Muhammad Shoaib, and in this lecture I will discuss the synthesis of aromatic compounds with respect to the disconnection approach. That is, how to disconnect aromatic compounds and how to synthesize them. First of all is the disconnection and FGI. Here it is an ester, and the esters are formed by a carboxylic acid or its derivative and alcohol. So this bond is broken down, it is disconnected to give a carboxylic acid and an alcohol. So where there is an ester bond, CO bond is disconnected to obtain in the starting molecules, which are carboxylic acid or its acid halide derivatives, and other one is alcohol. What is FGI? Here it is 4-amino benzoic acid. Neither amino group nor the carboxylic group is inserted or added to the benzene directly. NH2 is added by the reduction of nitro, so FGI, that is functional group interconversion, changes amino into nitro. And how to add carboxylic group on aromatic ring? That is also by FGI, by the oxidation of methyl or any alkyl group attached to the aromatic ring. Then which is to be disconnected? Here we disconnect nitro so that the toluene is obtained. Here one group which is methyl, it is ortho-para-directing group, and the second group is nitro group, which is meta-directing group. And both of these are present at para to each other. Therefore, we have to disconnect the meta-directing group so that we have ortho-para-directing group on the aromatic compound. So when nitration takes place, the CH3 or alkyl group will direct the nitro group to the para position. And if CH3, let's suppose CH3 is broken down or disconnected, so we have a nitrobenzene, and when nitrobenzene is alkylated, nitro group will direct alkyl group to the meta position. Therefore, and the correct disconnection is the nitro disconnection. Synthesis is simpler. First of all, toluene is nitrated, then it is oxidized so that alkyl group or methyl group is oxidized to carboxylic acid, then nitro is reduced to amino, and in the presence of alcohol, the carboxylic acid is converted into ester. Then the Friedal-Crafts Acylation. Here it is one group is methoxy and other is the acyl group. So the acyl is disconnected to obtain anisole and acetyl chloride. Remember that the group which is hard or which is difficult to insert or add, that is not disconnected. As we know that methoxy is not easy to add on aromatic ring, and that's why it is not disconnected and only acyl group is disconnected. There are two possibilities. When this bond is disconnected, One possibility is that benzene gets negative charge and carbonyl or acyl group gets positive charge. There can be another possibility that aromatic ring gets positive and carbonyl carbon gets negative charge, but this is not the feasible one as the natural polarity of aromatic compound. It is a donor synthon and carbonyl is a acceptor synthon. So the A is the required disconnection. And as a result of this disconnection, the reagents used are easily available: acetyl chloride and anisole. Here it is the synthetic method, and the reaction takes place in the presence of Lewis acid. Here it is BHT. There are three alkyl groups, two are tertiary butyl groups, and one is methyl group. So if we disconnect the tertiary butyl groups, then we get paracrysol and a tertiary butyl cation. Tertiary butyl cation is easy to add on the aromatic ring. And the second option is that we disconnect this methyl group so that 2,6-tertiary butyl phenol is obtained along with this synthon. But this is not the feasible one, as the paracrysol is easily available starting material. So in one step it is alkylated at ortho position of OH. Here is paracrysol. Here it is methyl group. Methyl group is also ortho para-attracting group, and OH is also ortho para-attracting group, but the effect of OH is more pronounced as compared to methyl. So this isobutene, in the presence of H positive, it is converted into a cation when it will attack here. So a tertiary carbocation will be generated, and the benzene or aromatic ring will attack on this carbocation to give this target molecule. There can be another possibility if we use tertiary butyl chloride in the presence of any Lewis acid. Here it is an interesting example. Here it is only one substituent attached to the aromatic ring, that is isobutyl. When it is disconnected from this one, we get benzene and a carbocation, that is a primary carbocation. And we suppose that here is some leaving group like halogens. So it is 1-chloro-2 methyl propane, that is alkyl halide, which can be used to alkylate this benzene. When we try to synthesize it, this alkyl halide, as we expect that in the presence of Lewis acid, this alkyl halide will be converted into a primary carbocation on the positive charge on this carbon. But when it is actually performed, the positive charge which we expect here, it is formed as an intermediate, but this hydrogen along with its electron pair, that is hydride, is shifted to this one, so that the more stable tertiary carbocation is produced by the rearrangement reaction of a primary carbocation. So the actual product is 1,4-ditertiary butyl benzene or the tertiary butyl benzene. That's why this disconnection does not work. So if instead of that alkyl halide we use this acyl halide by using Friedel-Crafts acylation in the presence of Lewis acid, then this acyl group is added and when it is reduced to this target molecule. So sometime as the situation shows that the reaction is very simple, but it is not that simple. So we have to do FGI before the disconnection. So before disconnecting this bond, we have to do FGA, functional group addition, functional group interconversion or functional group addition. These are the similar terms. So the carbonyl is added to here, then it is disconnected so that uh, the target molecule is formed or prepared by Friedel-Crafts acylation followed by the reduction of carbonyl compound. Here are some synthon, the groups which can be added to the aromatic rings. Alkyl can be added to the aromatic ring by using alkyl halide in the presence of a Lewis acid or any alcohol in the presence of an acid. Acyl can be added to the aromatic ring by using acyl halide in the presence of an Lewis acid. Nitro can be added in the presence of nitric acid and sulfuric acid. This nitro can be converted further into amine and many other functional groups. Aromatic compounds can be further substituted by a chlorobromosulfonic or chlorosulfonic group by the use of these reagents. Next, the changing of polarity. Nucleophilic aromatic substitution. The aromatic compounds usually do not undergo SN reactions. The reason is that if aromatic compound, that is benzene, it have a good leaving group, that is any halogen, and an attacking group attacks on it, the reaction is not feasible under normal conditions. Why? Because benzene, the aromatic compound, are rich in electrons. The leaving group, which is also a nucleophile, that is also electron rich, and the attacking group, that is also a nucleophile, which is also rich in electron. So there is a lot of repulsion between all these electron rich groups. So the aromatic substitution does not take place on aromatic compounds in the same manner as it happens in non-aromatic compounds. Suppose we want to disconnect this alkoxy group. We expect that we have this nucleophile and a leaving group here. Or in the second case, uh, that nucleophile can some other nucleophile such as amino or primary or secondary amine. We expect that we will get this nucleophile as an attacking group and this aromatic halide as a substrate. We expect that this nitrogen, lone pair of nitrogen, will attack on this aromatic compound and this leaving group will leave, but actually it is not possible. It is not so easy. So what we have to do for nucleophilic substitution reaction, there must be some electron withdrawing group such as nitro, preferably at meta position to the leaving group. It is nitro. A nitro group will attract withdraw electrons from aromatic ring so that this carbon will get partial positive and it will become an electrophile, and now any nucleophile can attack on this electrophilic carbon and the leaving group will leave. So remember that nucleophilic aromatic substitution takes place in the presence of electron withdrawing group, which can be nitro or any carbonyl. Here, here it is a target molecule. Here it is a nucleophile, diisopropylamine. It is disconnected, and we can say that it can be added to this aromatic compound or benzene ring by acid reaction. So when it is disconnected, Cl comes on its place, then the nitro groups are disconnected, so that we have this 1-chloro-4 trifluoromethylbenzene. And now let's see synthesis. 1-chloro-4 trifluoromethylbenzene, it is nitrated. CF3, it is meta-directing group, and Cl, it is ortho-para-directing group. So both will direct the incoming nitro group to that is ortho to the chloro, and that is meta to the CF3, that is trifluoromethyl. And this intermediate compound is obtained, and when it reacts with the diisopropylamine, the simple SN reaction will take place, and this amine will replace this chloro from this, and target molecule is obtained. And when we see its synthesis from the start of the reaction, how chloro and the trifluoromethyl is added, it is in detail. First of all, Friedal-Crafts alkylation takes place, so that alkyl group, that is methyl, is added. Then chlorination takes place in the presence of Lewis acid. It directs, alkyl group directs chloro to the para position. Then further chlorination without any Lewis acid. Here there is no Lewis acid, so this methyl is chlorinated and CCl3 is obtained. Then in the presence of antimony pentafluoride, this chloro is replaced by the fluoro, and then the reaction is similar, which we have studied. Here is another example. It is very interesting example, and it is of unique of its kind. When we disconnect here, then we obtain this 1-fluoro-4 trifluoromethylbenzene. This amino alcohol, which we will not study the synthesis of amino alcohol here. It is not the matter of our subject of this lecture. So why we inserted fluorine here? As we know that fluorine is very poor leaving group, but let's see its synthesis. Synthesis is very straightforward. This amino alcohol, the lone pair on oxygen will attack on this, and fluorine will leave. And then how this SN reaction takes place? It is due to the two factors. First is that trifluoromethyl, it is a very strong electron withdrawing group. It will withdraw electrons from aromatic compounds due to the high electronegativity of fluorine. And the second is the high electronegativity of this fluorine. it will withdraw electrons from this carbon, and this carbon will behave as an electrophilic carbon so that SN reaction takes place. Changing the polarity. Diazotization is another important way to synthesize a variety of aromatic compounds. How diazonium salt is prepared? Any aromatic compounds, uh, this R along with this line or a bond shows that this R can be present on any carbon of these aromatic compounds. Uh, Nitration takes place, nitro, and then this nitro can be reduced by using hydrogen palladium charcoal or in the presence of tin or HCl, so that amino is obtained. It is diazotized by using sodium nitrite and HCl. The HCl hydrochloric acid should be concentrated, and the temperature should be very low for this reaction, so that this diazonium salt is obtained. If we see this nitro is not a good leaving group. When we see this amino, it is not a good leaving group. But when we see this diazo group, it is very good leaving group, so that it can be converted into our different other substituted aromatic compounds by simple SN reactions. Here, when it is treated with water, we get phenol. So benzene or nitrobenzene or aminobenzene, that is aniline, can be converted into phenol by the use of diazonium. And let's see the disconnection of this target molecule. We know that this cyano can be added to the nucleophilic substitution reaction, but this nucleophilic substitution does not take place directly, so it is converted into NH2, which is after FGI it is converted to nitro, and then when this nitro is disconnected, toluene is obtained. Let's see its synthesis, which is our concern. When toluene is nitrated, it is at ortho. Remember that ortho and para mix, both mixture and both compounds will be obtained. So we have to separate the mixture of ortho and para product. When it is reduced, it is reduced to amino, and when it is diazotized, it is converted into diazonium salt, and when it reacts with cuprous cyanide, our required molecule, that is 2-methyl benzonitrile, is obtained. Similarly, this amino or nitro can be replaced by chloro, bromo, iodo. Here it is another example, saccharine. It is a cyclic imide as shown here. And first is the disconnection from these heteroatom next to the sulfur and nitrogen on both sides. So the bond disconnected is SN and the CN bond. And the required and the molecule which is obtained is carboxylic acid and the sulfonic group. By FGI, this carboxyl group is converted into alkyl group as shown here, and when this sulfonic group is disconnected, we get toluene. Now let's see its synthesis. Starting from benzene, it is alkylated, then it is chlorosulfonated, sulfonyl chloride is added, then when it reacts with ammonia, HCl is removed from here so that SO2NH2 is produced. Then by oxidation, this methyl is converted into carboxyl group, and when it is heated, dehydration takes place to give us this target molecule, that is saccharine. That's all about some basics of synthesis of aromatic compounds. Thank you.